Good evening, flight test. As promised, this is an overview of all the different files and system identification process that you'll need. So what I've done here on the right-hand side is I've made a brief outline over the different types of things that you need. Obviously, this is flight test 2, looking at flight data and system identification overview. So we're right here. I'm just giving you files, processes, programs, and so on, just so it's clear to you how to get all the files that you need, arrange them appropriately, find the right program that you need, and how to use them. And per your suggestions in class, there's a lot to go over, so I think this video overview hopefully is a little bit easier. But I'm going to start a little bit with a brief of the flight data overview. I'm sorry, the flight data file overview. And I have a directory here, which I'll find some way to share. The two important M files are this EAS4939 FT2 plotdata.m and then another one EAS4939 FT2 extract maneuver segment.m. This .asv and the other one, those are just autosave files, so you don't care about those. The four main files that you're going to care about that basically include all of the different tests are here. This EAS4939 FT2, this is the second flight test in the course. Test number 1, the first test flight, the second test flight, third, and finally fourth one. So this is one where I think we had 6 students fly, 4 students, and finally that last slacker student here on test 3. Test 4 was the test I conducted on a different day, but includes segments and maneuvers that you may want to use as well. All these other files here I'll describe a little bit later on. But basically the start of this whole analysis setup is 4 .mat files. These are .mats. These are the data from MATLAB. And then 2 of these other ones, the .m files, which will allow you to actually run them. So let's start running them. Actually, this doesn't have a good way of doing it. Let's do here. So we can see which one to run. Viewing and plotting flight data. So I will open up my MATLAB editor window, and you want to see this ES4939 FT2 plot data. If we scroll up to the top, I made a couple of changes since what you saw in class. So this still does a clear all. If you want to save something in the workspace, you can comment this with a %sign. And instead of the little switch statement at the top, I have the UI get file, which is maybe a little bit more convenient. And you'll see that in the top of the file, this select the EAS4939 FT2 flight data log. This is a file that loads whatever file name that you pick. It'll give you an error if for whatever reason it's not appropriate. And then it goes through and plots 4 different plots. This first one is the general aircraft performance, which shows basically the strip charts or the time series, showing in order controls, rate, command and response, angle, command and response, acceleration, XYZ, and then the airspeed plus altitude. The second one, you can ignore this one unless you're really curious about it. It's plotting the lift coefficient. And in fact, now that I think of it, all these numbers are wrong, so it's totally bogus. The third plot, the 1003, is just the raw GPS position. So this is no colorization at all. This just shows using the plot3 command, all basically the XYZ position excuse me, of the aircraft. The final plot that's done automatically for you is a plot the colorized GPS position. And I showed that this one uses the scatter3 command. And scatter3 takes in a X, Y, and Z. And then finally you can put this is the size, which I've left blank, and the color. And you might notice that Y is where I said X was. I'm plotting it this way just because of the northeast down convention. So this is the x-axis of the plot is really the y-axis with respect to the measurement. In that case, that's not a big deal. Well, I guess let's talk about this. Northeast down, right, is the convention. And just so when you're plotting, it looks like north is on the vertical axis. That's why we do it this way. All right, there's a couple of switch statements that you care about. Well, let's run this first before we do anything. I think right now the switches here are only in terms of the colorization and the time segment. And I think that all the time segments are set to all. So let's plot this first, or the run this rather. we'll click here. It might ask you to change folder, and then it'll pop up with this dialog. Here again, we have select the EAS4939 FT2 flight data log. We're going to pick the first one, the 41 megabyte one, and MATLAB will churn and process and should result in 4 data plots, only 3 of which we care about. All right, and let's look at them in order. Maximizes here in the available space. So there's this ongoing issue with the legends and where they exist. But anyway, so part of the reason this file is so much bigger than the other ones is that we armed the aircraft, and that is the signal for it to start logging the data file, or logging to the SD card. But from 800 seconds to 1600 seconds, which is really quite a long time, it's just sitting there logging on the ground. So it really is not a longer flight. It just happens that it was logging for a long time. I discussed how do you figure out if the aircraft's flying or not. There's a whole bunch of things, but let's go over all the plots in detail. Well, maybe a quick overview. The top plot is actuator controls. So you have aileron is blue, orange is elevator, yellow is rudder, purple is throttle, and I give you nav status here in green. Keep in mind you can go in and you can change these plots however you want to, but if you want to see what mode the aircraft is in, I've just left this as raw, whatever the PICSOC comes with. But when it's at 1, I believe 1 is attitude mode, maybe? What is this? I think so. We can work this out, right? Because in some cases here we're spending a lot of time. Actually, no, it's rate mode, right? So the aircraft starts off, takes off here in rate mode, which is at 1, and then it goes down to this navigation mode, which, let's put a data cursor on that just to figure out what it is. Yeah, so it's 0.3, right? Which is, normally it would be 3, but anyways, so when it's 1, it's in angular rate tracking mode. When it's in 0.3, this little green line here in the middle, that's in navigation mode, and it'll occasionally dip down here to, let's see what it does, to 0.1. When it's in 0.1, it's an attitude reference. And we can check that by zooming in on a portion of the plot that shows all 3. Here, for instance, we actually have a slightly different one. How about here? This is a segment that shows the aircraft going through all 3. When you look here in this middle plot at this dashed blue line moving, that is the pilot's attitude command. So this is roll angle, phi command here on the legend, in dashed blue, followed by the phi, which is roll angle, in solid blue. You can see that the pilot is making a command, the aircraft has some delayed response to that. If you see the dashed line move, that is an indication that the aircraft has attitude reference. So this guy, this green line here on the top chart goes down to 0.1. This guy's moving, it shows the attitude reference. And then if it goes to navigation mode, it still has that attitude reference, but we're ignoring that, right? This is one doublet and another doublet approximately right here, which is the aircraft in a roll angle mode. This is where the aircraft rolled upside down, so it really wasn't a complete doublet, right? We only rolled one way and rolled right back up the other way, put it back into nav mode. This is maybe a really aggressive one. To zoom out, I have clicked on this and I shift. So click and hold, or hold, click down, hold shift down, sorry, and then as you click it zooms out. So without getting into too many details here, that is an overview here of this top plot, angular rates here, roll, pitch, yaw, PQR, attitude, phi and theta, and then this is accelerations. So if you want to see how many G's we're pulling, this is one where it looks like maybe we were recovering from a roll. We pulled about 5 G's in the recovery to that. So it was a pretty healthy maneuver. Airspeed starts to increase. The dark blue is going to be the measured airspeed, and the cyan is going to be the GPS speed. So if you look at them as we're orbiting around, you should see that the airspeed remains not constant, right? But airspeed remains somewhat neutral. I get that all the time. And ground speed moves around, and this is the effect of the wind. A here is altitude, where we're mostly holding altitude divided by 10. All right, that's this guy. Let's move on to the next plot. This, as we mentioned in class, is the GPS plot. It just looks and gives you an overview of how the aircraft is flying around. And the last one is the GPS plot using the scatter3 function. And this one gives you colorization with respect to whatever it is that you want. And you can zoom around and obviously you can do the windowing to select a partial preview of this. I show you that in class, so I don't think it's worth spending too much time on at this point. So let me go back to our outline here. So let's talk about extracting maneuver segments. I could do no color. So we're here if you're following along. Right? It's working not how I wanted to. Okay, close. All right, extracting maneuver segments. Let's look at an easy plot. So we'll go back to this, the EAS4939 FT2 plot data. We'll run this again. It's going to run this UI get file command. And let's click on FT2 test 2. So it'll churn a little bit and finally give you this result. It's going to be a long video. Here, I want to show you these guys together. So I want to extract a particular maneuver, right? This is FT2 test 3. This is where only Chad was the one flying. This looks like it's a roll angle doublet here. It was not a bad one. And you can see that the nav status is at 0.1, so that's okay. So let's do this. We're going to do 821 maybe, all the way to 829. 821 to 829, that's the one that we care about. So we open up this second one. Go back to our editor window, and then you might not have as many files as I have, but whatever. 821 to 829, we happen to already have those, right? We had the notes that we put in class, but here in maneuver T start time, 821, type in 829, and you can bookkeep these however you want. This is going to find the indices of the time vector that correspond to something that's greater than maneuver T start time and less than maneuver T end time. And you could do other things, like you can put this less than or equals to. We'll just save that, so I'll send that to you. So relative to what we did in class, I shift this around a lot because I didn't like how the capitalization was working. So now everything that you get here in ft2 time is now fdata.time, fdata.elv. And the reason I want to do that to you is if you're typing this up and you do fdata. You can do tab, and then you scroll down through all these different options. So it's a little bit nicer when you're trying to look for something in particular, and then it helps disambiguate it. So when I'm going through and doing the extracted maneuvers, I don't have to worry about multiple renames, because time here is an array within fdata structure, and time there is just something in the workspace. And I can select only a portion of that, right? With these indices, a portion of time to dump into the workspace. So this is already pre-named, but the naming convention that I'm using is FT2, right, the flight test 2 for the whole class, test 3, the test within flight test 2 campaign, and fee command maneuver 1. This is already preloaded to Chad's command. When you run this, it will generate this file within this directory. I think, I'm not sure if it already exists or not, but anyways, we'll run this, and we can load it up and check to make sure that it exists. So this is the wrong window, sorry. Here we'll go back. In my case, it is, I'm sorry, I was in the right place, I think. Here it is, FT2 T3 fee command maneuver 1. And you click the timestamp here, 10:14 Sunday evening at 10:59 p.m. That's the one we just generated. All right, so that's the way you can do individual ones. And assuming we've extracted this, let's see if I can be a little bit better about how we do this. All right, let's go on to using Cypher for system identification. The first step is to do the download and install. And I should have prepared this ahead of time, but we'll try this. AIAA.org. Oh, of course it's down. Okay, so AIAA.org is down for some reason. In which case I'm going to ignore this, and I will probably, if I don't send you instructions for how to download and install, then I might just send you the 300 megabyte exe directly. All right, let's talk a little bit about the Cypher data structure. Or it's a directory structure. Direct data structure is within that, and it's different. So the directory structure that I have here is in my other window. I have this on the root C. So Cypher data is a directory that's within directly my my C. So it's not in users, documents or anything like that. And the reason is I think Cypher sometimes has problems with really long path names, which is the whole directory. If you're this is the path, right? If there's a whole bunch of things here, it could have trouble with it. So just precautionarily, I have Cypher data as a directory, EAS4939 is within there, and then FT2 is a subdirectory. Their names are kept short. I have several directories here. There's a database, a jobs, a plot, and a TH. I don't really use these ones. Oh, I broke it. I don't really use the jobs and the plot too much, but the database, if you open it up, it has these two files that correspond to the Cypher database. The time history files are empty currently, right? Because all of the stuff that I'm going to send you and the stuff that you're going to generate is going to go from in a MATLAB, wherever your MATLAB file is. And you can choose to have them all in the same directory. But I'm going to copy all of these, all these .mat files, actually not everything, rather, all the maneuver segments. I'm going to copy this, and I'm going to throw them in this directory. And I didn't explain what all of these were, at least not in this video. In the class, I did an overview of these when I was flying my flight test 2, test 4, the one that I did alone. I did all the frequency sweeps. I pre-did all of these maneuvers for you. And you can go in and look at the time history, right? If you do this plot data M file and you look at this one, you can see where all these come from. But I just extracted them for you for convenience for Cypher. Anyways, so we went over the Cypher directory structure, and let's load up Cypher and look at creating a new database. So just for the purpose of this tutorial, we're going to go here to Database and Database Manager. Click on that. And I think this one here, this gear icon, also does the same thing. But I already have this E4939 FT2. But if I want to create a new one, which we'll do here, we'll do new here. And the database that we want to do is called, let's call it tutorial, right? 4939 FT2. You can name it whatever you want. The other name that I had is E4939 FT2. You can feel whatever you want to do this. There's a configuration. I think we leave that default. There was some place to indicate an airplane, but that might be deprecated. So if you're loading this up for the first time, you might have to manually go through and pick. So you browse to wherever you want to actually do all your database, for instance. So FT2 here, database, select folder. So nothing really changed. Anyways, we do apply. Oh, so what did I do wrong? Database name must be fewer than. Oh, so I have too many letters here. F2 it might have been. Apply. Okay, so now it has to be 8 characters. I think it's a either old format or whatever it is. They haven't updated it. But anyways, T4939 underscore F2 default was created. If I OK this, the new database already exists. And if you wanted to prove that to yourself, you go here to the database folder. And here's our new database that I just created. It's tiny because it doesn't have anything in there. This is the data structure that it works off of. But anyways, that's irrelevant. So we did creating a new database here. Change this colorization. And now let's look at what I had. The first thing that I did in Cypher for you guys is creating a frequency response, or doing the frequency response identification with this program FreshBid. If you didn't see me already, that's when I clicked on this, this big F, and it goes to here. So if we browse, there's nothing there because this is the first time we did anything. So we're going to have a whole bunch of things to do, but let's say we wanted to look at Chad's file, right, or the Chad's doublet. We're going to do select something. We can call it whatever you want, but let's say T3, right? It was the test number 3, and it was P command 1. Is that too many? Yeah, I think that's too many. P command 1. Right? We can name it whatever we want. It's a good idea because we can do a lot of these to get into a consistent naming scheme. But here's what I selected for now. Underscores prohibited, of course, fail. T3 P command 1, and it asks, it's not found, do you want to create it? We say okay. This is test3 roll rate command doublet number 1, because it's possible that you do multiple roll command doublets as I did in test 4. Inputs, there's no pre-existing name, so we're going to put AIL, right? A-I-L, and then here P. Again, this is a frequency response, right? You're looking at, there's some input to the system, and that is ailerons. There's some output, which is roll rate, and we're trying to figure out what is the frequency response model that connects between them. So we'll go next. This one is in the time history data. It's asking you, where do I find the time history that corresponds to this? If you browse, because you set up your directory name, it already knows to look here, and it's ft-t3 fee command. So I guess I already did a mistake, right? This is supposed to be fee command, not p command. But either way, so if you caught it, good on you. We can change this, go back to the case setup. So this is roll angle doublet. And we do that, that should change it here. So maybe with just the name has to be changed. Anyways, browse there. Fee command maneuver 1. If you do plot right now, it'll give you an error. Well, this is flight test 3, number 1. We plot. It gets you this error using th file. And the reason that happened, right, is because this time history format was incorrectly specified. So we go to MATLAB. Make sure you click on number 10, MATLAB. When you do plot, now it reads this file and gives you all these different options. And look at the two that we care about. We care about P. We plot that. It looks like roll rate goes, one direction, other direction, third direction. That's pretty good. And look just to make sure at what phi looks like. This is clearly a doublet, right? Plus or minus 30 degrees. It's a great job. Anyways, so we do that. We go next on this one. Controls definition. You want to pick, these are all the different things that are in the, all the different pieces of data, or really data vectors that are in the file. Aileron is AIL. Sometimes it could be channel 1, channel 2, right? It could be not obviously named. Units of radians, which is approximately close. And P, same thing, we do P, units of radians per second. Next, asking you for which responses. We want to do all of them. We can ignore this. And here, we're at 24 minutes here on this video. We're going to select all these guys, and 1.1, 1.5, 2.0, 2.5, and 3.0, right? If you adjust this, what was the issue there? Windows C. I'm not sure what that was. Normally it should let us do 2.1. Okay. that might be something unique to this. Okay, so next, it gives us a couple of warnings. Again, its system identification doesn't work great if you have just a single one, but we're going to go through it just as an exercise. Then I clicked on Save and Run Batch Free, right? The frequency response estimation. We sit and wait for it. And eventually it'll say batch complete, no error detected. That means we are done here with FreshBid. I'm going to kill this and then go on to the next one. Right. Our next thing is we're going to do the composite averaging. For composite averaging, we click on this C here. We run the program composite. We browse. Nothing there, so we have to do the new one. And I forgot what we called the other one, right? But it was something like T3 P command 1. And obviously we made an error here, so we can, you could do phi command when you're actually doing it, but we'll leave it consistent. It's not found, so we're going to create it. We're going to click on here, click on free and browse. So this is looking for, remember that composite has to take an input. We've computed the frequency responses using 5 different window functions, and now this tool just does the averaging. The full version of this program does all this stuff automatically, right? So you don't have to worry about this step. But I'm not going to provide a $1,000 license for each of you guys. No offense. Anyways, click on here the different ones. I clicked on inputs, selected aileron. Why did I do that? Oh, sorry. And the outputs, P aileron, loaded that. I want to use all the windows, right? So I checked my input, my output, and I want to use, in the process of doing this composite, right, or this averaging, I'm going to use all the different windows. If I go next, case input and output names are not the same. What happened there? Uh-oh. This happened last time, but it didn't actually cause an issue, so we'll see if that actually is the case. Not all the same. It's probably worth dwelling on this very briefly just to make sure we didn't screw something up. Oh, I see. The problem is there's a capitalization inconsistency here, the output prefix. So that was my error when I was doing the input, which is why it's good to write this down. Not all the same still. Now here. Now we should be good. All right. Now we do all. Next. And you save and run batch. So this is just doing that portion where it's doing the averaging for the windowing and producing a single frequency response between aileron to P that accounts for a wide range of frequency validity. So assuming this step works well, we're going to assume that we run composite to successful completion. I'm going to kill the color, and it's taking longer than expected, but I'm going to presumptuously go on to the plotting frequency response. I wonder if maybe we should not have just clicked so aggressively on those error messages. And remember that if this screws up, I still have the database that I generated in class, so I can show you that in case we have an issue here. I'm actually going to pause the video here just so we're not sitting here staring at this too long. All right. In frustration, I clicked on exit no save, but it says batch complete, so I'm assuming this is good. All right, so we're back to Cypher here, and we're going to click on qplot, which is here. This is I think there's a couple ways to get to it. All right, tools, qplot, or you can click on that. And qplot is what's called quick plot. This is a way to very rapidly assess, or with like a cursory overview, what the frequency response looks like. T3P command, right? This is the input file name that we had. Com is the composite output, right? You can click on all these other ones. ABCDE means it shows you all the different windows and from AL to P. So we're gonna load this one, and you can choose to do some math on it, right? And frequency shifting, but we don't care about that currently. You can choose to do this, but if you just click through, it'll generate a plot. Here's a frequency response plot. It shows you the three sets, the magnitude, phase, and coherence, all plotted with the respective frequency. What we care about here is looking at what is the general shape of this. I messed that up. What is the general shape of each of these curves? And what is the range over which they're valid? So remember, it's really important that we have good frequency, good coherence in the frequency range that corresponds to this corner or the characteristic frequency. One doesn't always give it to us, but we're going to say that this is close, and it's not bad currently. So maybe we would want it to extend outwards by, instead of between 20, 30, right, we want it to go up to 40 or 50 radians per second, but this is what we have. All right, so that's qplot. And let's go on to the last step in Cypher, which is really the subject of the entire exercise. And that is to do this state space system identification using the derivative or deriv ID. That's this one right here. If you go the one equals fx4, click on that. This is a derivative. Case name, browse, doesn't have anything anymore. And we can do different ones. So or different methods of naming. So let's do this one. We're going to do T3 P1. Sorry, Phi1, right? This is from test 3. This is a Phi, maybe even Phi doublet. And then, how many does that use? That's 3. And then roll 1. I think you might have more, right? This is the single dimensional roll mode. You can also just call it roll. Next. It's not found, so yes, we want to create it. Next. So we're going to click through this. Yes, we want to make all these things: the model structure, the M matrix, F matrix, G matrix, tau matrix, H matrix. Now we're asked to start setting up the parameters associated with this. So the state is going to be P. That's the single state that we have. The output is P, so the state and the output are the same. And the control name is AL, right, aileron. Next gets us to the response selection. We want to do all these. Not sure why that's not working. Sensor coefficients, we're going to assume that the sensors measure perfectly. So we're going to ignore that. Channel assignments, we ignore. And now it's this frequency response selection. We click on this ellipses, T3P command, com1, let's do that, and plot this here, quick plot. The important step here is to determine the frequency range that's where the coherence is high. What is the acceptable frequency range? And as a result, what are we going to put? We're only going to fit the model over the frequency range that appears to be valid. And this is maybe 25.4, right? Or let's call it 25. That is the frequency range that we like. And so we're going to go next. And here's where we do the matrix setup. We're going to assume that we don't have a moment of inertia measurement, so this M matrix is going to be unchanged. If you go to the F matrix, there's there's 4 different things you care about here. Normally, if this is a large matrix, you'll see 4 of these text boxes or check boxes, right, times however many parameters you have. But we just have one thing, right? It's P to P. P is the state to P output. Or I'm sorry, this is how P relates to the derivative of P. And this term is just LP, or L sub P. This component is whatever fixed component you want, and this is with a free component. Because remember, this system identification process is actively looking for the value of the parameter the value of the coefficient that solves the estimation problem, right? So how can you mess around with these parameters so that the output data matches the simulated data? We're going to leave this as 0, and this we're going to just seed it as something, -10, right? This is just our initial guess. I'm going to click on this button. So by clicking on this button, we're telling the algorithm, this feasible sequential quadratic program, that this is a parameter that you can change, right? Normally, if we're positive that this is like -20, and we don't want the algorithm to consider it, we then uncheck that. But we'll leave it checked. We'll go on to G matrix. G matrix here is what you might know as the B matrix. And this doesn't have that free component. This just has your initial guess. I'm going to say 10 as our initial guess. And the name of the parameter here is L delta A, or LDA. In tau matrix, again, we're going to say we need to estimate this. You can call it tau A, and 0 is fine. The H of S, we're going to say this is 1. So this is what is there sort of a algorithmic relationship between these measurements of P? Is there something? But we're going to say it's 1. P is just equal to P, and there's no derivative issues here going on. Right, next, simple constraints, we're going to ignore. Right, flexible constraints, we're going to ignore. Constraints are ways to really shape the effect or the behavior of the sensor optimization or estimation algorithm. Did I say sensor? I meant the system identification. Case summary, we're going to next. Here is a summary of what your M, F, G, and tau matrices look like. And it gives you, I think, some error, right? The average cost function. So when we did -10 and 10, it computes, what the cost function is. It's comparing the output of this model that we're identifying right now to the flight data. And the cost is really high, meaning that it's a very poor estimate. Input data looks great, and it asks you for iteration, because you can do 1 to 1,000 or however many iterations you want. We're going to click on this, start iterating, and we got 31, right? Less than 100 is pretty good, less than 50 is decent, so this is not terrible. Remember that we can sort of skew this process by selecting a very narrow window. But we click next. You can here do view all frequency response values. This, if you want to output it to something, you can do it that way. Final values of all the matrix elements. This, if you're looking at a state space diagram, this gives you the full F matrix. Because it's a single value for us, right? It's a single dimensional problem. It's not that interesting. And calculating the sensitivities. So this tells us this is the value, and the Kramer-Rao bounds and the Kramer-Rao percentages. This, we want to have these below 10, right? So generally we want to have, these are humongous values, so it looks like these are probably not great values. If we generate the plot here, and this is how it looks like. It seems like it did an okay job. It's having trouble with the sensitivity, largely because we really didn't get this taper. Here's the flight data, right? And we really didn't get the roll-off, so it doesn't know, right? It has to pick a corner frequency, but it doesn't really know where that is because we really didn't select the frequency range wide enough to show that roll-off. And that's a problem. And arguably, there's good reason to say maybe you should go to where it's lower coherence, even just to get that little bit of a roll-off. Otherwise, it's really hard to match. Because this looks like it's decent results, but who knows about the actual validity. Then you can click Next. Here, this is really important. And you can choose to save this. If you don't do this step and you exit, I think you lose this. But we're going to go here and store this model structure and save. I'm having weird GUI issues, and hopefully you don't have that. In any case, so that is a summary of how to use derivative. It is more interesting when you do multiples, and I'll tell you here. Actually, it's not here in other places. So when you want to do multiples together, as in multiple inputs to the frequency response, I'll show you where to do that. GUI issues. Here you can select different ones. So you can choose to say, hey, I want to do multiples. And if you click, for instance, fast 1 and fast 2, those are, doublet 1 and doublet 2. You can do frequency 1 and 2. You can add those things here. And again, sorry, I have GUI issues, but normally, all right, there you go. So normally it should present itself here. You can do up to 3 and stack these together. When you stack more together, it helps result in better identification. I might make a second video that shows you different sweeps or looking at identification with sweeps, but for right now, I think this is a summary of how to use Cypher. I'll very briefly go over this. Oops, I don't intend for this to be the actual report requirement, but just so you know, right, I'll go over this better later on, but I want your report to include an overview of the flight test. What did we do? What was the purpose of it? Give a really good briefing. Tell me about theory, right? The role of flight dynamics, why they're so important, how to identify them, give me the equations, and then talk about system identification. What is the process to go from a measurement of input and output to estimating what those actual coefficients are? I want you to talk about the flight test procedure. What did we actually do? You know, what went right, what went wrong? Give me a narrative that I can follow. With regards to system identification, I want you guys to do 3 main setups. So you notice that I was doing the different naming here in Cypher, but I want you guys to tell me or to show me frequency responses associated with the roll rate doublet that you did, the roll angle doublet that you did, and then maybe multiple, right? And you can choose to use mine, other students, or whoever, right? But multiple P command doublets, multiple phi command doublets, so now we can stack them together, and multiple here means 3. And then you can use frequency sweeps as well. So you're supposed to do this system identification process, meaning you go through all the FRESBID, composite, and derivative, right? This state space identification for 6 total times, and then you have to find a good way of presenting that. The derivative or the sysid coefficients, that's going to give you parameters, and maybe you have a table that says, from 1 to 6 here, how all these vary. For frequency responses, maybe you want to go to qplot and plot these on top of each other, right? Because you can select multiples. We'll go over more of this in class. The last thing that I'm mentioning right now is the appendix flight card. Make sure you give me a digital copy that's in your report. If you want to attach it separately as well, right, it should be in the report, but you can also send it to me as well. That's very helpful. All right. This is 43 minutes long. It's already a much longer video than I intended, but hopefully it's good that you can follow it and work through how to solve Cypher problems. As always, let me know by phone, text, or email if you have any questions.